The following is the video solution from JSDT Solutions. Question 8, and just note that in question 8, 9, and 10, we need to give reasons for our statements and calculations. So question 8, 8.1 says, in the diagram, O is the center of the circle A, B, C. And then they tell us that AB and AC are chords. OB and OC are joined, and we need to prove the theorem which states that angle BOC is twice the size of angle BAC. Okay, so to prove this theorem, the first thing we'll do is we're going to draw a line dividing this shape into two triangles. So we're going to draw a line from A to O and extend it. Okay, you can extend it to the end, that's also fine. So you can just see it as drawing a diameter, okay? And I'm going to go ahead and name these angles. So I'll go ahead and call this angle A1, and that's angle A2, and then this would be angle O1 and angle O2. Make sure to write down any constructions that you have made. So this is just being drawn to, I'll just call this point P. It doesn't have to be this long, it can just be an extension of that, but it's also fine like that. It still serves the same purpose. Okay, so I've drawn a line from A to P passing O. Any description of that construction will do. Okay, so now that we have done that, this is what we have created. We have two triangles here. So this triangle over here, triangle AOB, and we have this triangle over here, triangle AOC. Now, in these triangles, we have exterior angles. So this is where we'll start off because our focus is on these center angles, this one as a whole, and of course that angle. So we'll go ahead and tell them that angle O1, because it is the exterior angle of this triangle, angle O1 is equal to the sum of the two opposite interior angles, which would be angle A1 plus angle B. So let's go ahead and tell them that angle O1 is equal to angle A1 plus angle B. And this is because of the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So we can just say exterior angle of a triangle. But now notice something about this. In this triangle, from O to A, that's a radius, and from O to B, that's also a radius. So it means that they are the exact same length. So if they are the same length, then this is equal to this. And so what that means is we're just going to tell them, this means that AO is equal to BO because they are equal radii. And if those lines are equal, the angles opposite those equal sides would also be equal. So angle A1 is actually equal to angle B. So we'll tell them angle A1 is equal to angle B. So this means we can actually update this equation. And of course, the reason is angles opposite equal sides are equal. Okay, I've just pulled that up. So now that we have that they are equal, we can actually update this equation. Now our focus angle is specifically going to be angle A1 because it is part of the angle they're asking us to prove. So we're going to update this equation. So this is angle O1 is equal to angle A1. And in place of B, because they are equal, we will say plus angle A1. So this is therefore angle O1 is equal to 2 times the size of angle A1. And so this is what we have right now. Okay, so now looking at the other triangle that we have, which is this triangle over here, see how angle O2 is the exterior angle of this triangle. So we can tell them angle O2 is equal to angle A2 plus angle C for the same reason as well. So angle O2 equals angle A2 plus angle C, and it's also because of the exterior angle of a triangle. And now in this triangle, we also have the same situation where we have OA being a radius and OC being a radius. So if they are equal, we'll tell them that OA is equal to OC because they are equal radii. And now that they're equal, it means that these angles are equal. Angle A2 is actually equal to angle C. So we'll tell them angle A2 equals angle C because of angles opposite equal sides are equal. Okay? And now we can update this equation, angle O2's equation. So it means that angle O2 is equal to angle A2, we're keeping the focus on the angle A, plus, and in place of angle C, we say angle A2. And now that we have this, we can say angle O2 is equal to 2 angle A2. Okay, so this is what we have. And now the final step. We're looking at these and just focus on what they asked us to prove. They asked us to prove that angle BOC, this center angle, which we can now see is an addition of angle O1 and angle O2. So if you add them together, you get BOC. And it's equal to twice the size of angle BAC, which is this angle over here. It's A1 plus A2. So that's what we're going to do. We're going to add these equations. So angle O1 plus angle O2 is equal to, and we're just looking at the equations. Angle O1 was equal to 2 angle A1. So that's 2 angle A1. And angle O2 is equal to 2 angle A2. Okay, so we know that when we add these angles together, they give us this angle BOC. So that's BOC is equal to, and we have a common factor of 2 here. So we can take it out as a common factor, and we get 2, and then open a bracket. And what are we left with? We're left with angle A1 in the first term, and in the second term, we're left with angle A2. And now you know that if you add these two together, we can see them at the circumference. They make up that angle BAC that they are referring to. So this therefore concludes that angle BOC is equal to twice the size of this is angle BAC. And that is how we prove this theorem. Moving on to the next question. Question 8.2 says, O is the center of the circle CBE. DB is a tangent to the circle at B, and then EC produced meets BD at D and intersects OB at F, as we can see over there. And then they tell us that CD is equal to CB. Okay, so we'll have to keep that in mind. And then OE and EB are joined. Okay. And lastly, angle B3 is equal to X. Okay, and the first question is, name with reasons 2 other angles equal to X. Okay, so looking at where X is, we need 2 other angles equal to X. Well, first, they told us that these 2 sides are equal, right? CD is equal to CB. So if these are equal, we have a nice isosceles triangle. Okay, angles opposite equal sides are equal. So it means that angle D is also equal to X. So we can tell them that angle D is equal to X because we have angles opposite equal sides. And then what else do we have? So this is X over here. How does this move? Okay, they told us that DB is a tangent. So if DB is a tangent to the circle at B, then this is the chord that we have, right? The angle between a tangent and a chord is equal to the angle supported by that same chord at the circumference. Okay, so that angle over there. So angle E2 would be equal to X because of the tan chord theorem. So tell them angle E2 is also equal to X because of the tan chord theorem. And that is our answer, and that was for 4 marks. Moving on to the next question. Question 8.2.2 says, express angle EOB in terms of X. Okay, so let's look at that angle. EOB is the angle over here. We're going from E to O to B. So this angle over here. Okay, it's the angle at the center. So immediately, we can just try and use that theorem. And we've just proved it in the previous question, in the first one. So the angle at the center is twice the size of the angle at the circumference as long as they're supported by the same chord or arc. So which other angle at the circumference is also supported by BE? That will be this angle over here, angle C2. So since we know that, this is what we need to find. If we find angle C2, we will find angle EOB. Okay, so looking at angle C2, you can see this triangle that we have over here. This is an exterior angle. They're using concepts that we just used to prove that theorem. Okay, so the exterior angle of a triangle is equal to the sum of the 2 opposite interior angles. So it means that angle C2 is actually equal to 2x because it's an addition of that x and x. So let's start there by telling them angle C2 is equal to 2x, and this is because of the exterior angle of a triangle. Okay, and now that we know that, we would also be able to tell them that if this is 2x, then this angle over here, this is the angle at the center. It is the one that is twice the size of the angle at the circumference. So if this is 2x, this is 4x. Okay, that's the bigger one. So tell them that this angle that they asked us to find, angle EOB, is equal to twice the size of angle C2. So it is equal to 4x. Okay, it's like substituting. And that is because the angle at the center is twice the angle at the circumference, supported by the same chord or arc. Okay, and that is our answer. Moving on to the next question. Question 8.2.3 says, determine with reasons the size of angle B2 in terms of x. Okay, so this is what we have. And to find angle B2, since it's this angle over here, we're just going to have to see what exactly angle B2 is. Where is it? We can see that it's at the circumference, but unfortunately, it's not being supported by a chord. Okay, as you can see, it's being supported by CO. That's not a chord. That's at the circumference and at the center. So we can't really apply any theorem like that. What else can we see about this? Also, just check the mark allocation. It's only 2 marks. So it's something that's supposed to be a one-step process. Okay, so here's the thing. Notice that O is the center of the circle, and from O to B, that is a radius. Now, DB is a tangent. Now, what do we know about a radius and a tangent at their points of contact? They will be equal to 90 degrees, okay? So angle B2 plus x should give us 90 degrees because the tangent is perpendicular to the radius at the point of contact. So you can't start off like that. Angle B2 plus x is equal to 90 degrees. This is because we have tangent perpendicular to radius. And then angle B2 is therefore equal to 90 degrees minus x. And that is our answer. Moving on to the next question. Question 8.2.4 says, show that DC equals CF. So let's just get rid of these and let's just see what they're referring to. They want us to prove that CF is equal to DF. So this is equal to this. Yeah, not the usual type. You would have expected that if they were asking to prove 2 sides were equal, we would somehow have an isosceles triangle. But it's fine. Let's just look at how this could be possible. Now, remember, we already found this. It's always going to be helpful. The previous question will always be helpful. We found angle B2 to be 90 degrees minus x. We'll keep that in mind. So how can these 2 lines be equal? How can that be equal to this? Well, they're definitely not using anything about proportionality or the midpoint theorem because we do not have a line drawn parallel to one side of a triangle. So we're going to have to look at this like this. We may not be able to directly prove that CD is equal to CF, but here's the thing. We can still work with an isosceles triangle. If we can show them that CF is equal to CB, because we already know that CB is equal to CD, then that will make these 2 equal. So what we're required to prove, what we're going to focus on is, we're going to try to show them that CF, or we're really just checking to see if CF is actually equal to CB. And if these 2 are equal, they already told us from the start that CD is equal to CB. So notice, if these 2 sides are both equal to CB, then it would mean that they are also equal. And that would prove that CF is indeed equal to CD. Okay, so this is our goal. Our goal is to prove that CF equals CB. How do we show them that this line is equal to this line? You can look at the triangle they are a part of. So they are part of this triangle here, CFB or CBF. If we want to show them that these 2 sides are equal, then show them that their base angles or the angles opposite those sides are equal. So let's find angle F2. That's the goal now. We need to find angle F2. So let me just write down what we have so long. We're trying to prove that CF is equal to CB, and this will really just help our case. So we're required to prove that CF equals CB because we already knew that these two were initially equal. CD was equal to CB. And now we're just trying to find that angle F2. Okay, so we're just trying to find angle F2. So how can we find angle F2? Well, we could go through this whole thing of finding it here, which is fine. You can use this to find it. But I'm also just seeing another easier way to find it. Use this bigger triangle over here, because we know that here the radius and the tangent are perpendicular. So that's 90 degrees. This is x, and we just have to find angle F2. So we can simply tell them that angle F2 is equal to 180 degrees minus 90 degrees minus the x, because the angles in a triangle add up to 180 degrees. Okay, and then angle F2 is actually equal to 90 degrees minus x. And that makes perfect sense. Okay, these two are actually equal. So if angle F2 is equal to 90 degrees minus x, that means that angle F2 is equal to angle B2. So we know that it's equal to angle B2. And because of those angles are equal, because these two angles are equal, that makes the sides opposite them equal as well. So this will be the converse of that theorem. Angles opposite equal sides are equal. So we can conclude that this means that CF is actually equal to CB. So therefore, CF equals CB. And you can say converse of angles opposite equal sides are equal, or you could just say sides opposite equal angles are equal. Okay, and now that those two are equal, here's the thing. Here's the whole point. We can tell them if these two are equal, we already knew initially. We'll tell them, but remember, this is what was already there. This is what we're just required to prove. But we knew that CD was equal to CB. So here's the thing. They're both equal to CB. That's equal to CB and that's equal to CB. So that means they are equal, since they are equal to the same side. So CF is therefore equal to CD, like they asked us to prove. Okay, of course they called it DC and CF, so you can just say that as well. DC is therefore equal to CF, and that is our answer.